Any idea what you see here? This is a sample of cancer tissue. The growth of a tumor can be measured by counting tumor cells with increased levels of a certain protein. This can be done by counting those cells in sections of colored tissue, which show these increased protein levels with a certain color. In this example, the brownish cells have an increased level, and the ratio of the brownish and bluish cells tells us about the tumor growth. This really plays an important role for diagnosis and treatment monitoring of cancer. Imagine now how many cells you could count while I was talking. So what's that to do with a conference about event-driven microservices? There is a lot of such image-based questions in life science research, and this is opposed by a rather poor grade of digitalization for image analysis in this field. Since the end of 2018, we are on our mission to change this. This was when we kicked off the development of our image analysis platform IKOSA. Back then, most probably on a rainy autumn day in our office in Graz, we took a single decision that should have really a great effect on our work during the last 2 years. This was when we jumped headfirst into implementing domain-driven design, event sourcing and CQRS in a microservice architecture with a team that was really all new to the topic. Good morning or good evening, you never know that for sure for an online conference. My name is Jakob Hatzl. I am lead developer for IKOSA and head of software engineering at KML Vision. It's really an honor for me to be part of this great panel of speakers at this conference, and my talk will definitely be on the more pragmatic side of the spectrum of the talks you will get during the next 2 days. Being rather new to the topic when we started development of IKOSA, I'm really happy to share our journey and most importantly what we learned during the last 2 years of applying CQRS and event sourcing in a microservice architecture when we implemented an image analysis platform for life science research. Life science research tackles tough and complex problems. There is really a huge variety of fields like dermatology or pathology or pharmacology, and what is common to all of those fields is the use of images as a basis for the research. Digital imaging as a tool is, however, not everywhere, but still commonly used in research. But the industry is really far from having standard tools for working on digital image data or even having software-based workflows for image analysis. So besides the actual research questions, there is a lot of other challenges to solve for our customers when it comes to automated image analysis. First of all, one question is the size of the images. When you think of glass slides that are often used in analogous microscopy, those most often get scanned, and the scans of such glass slides can have resolutions of up to gigapixels, so images having 100,000 pixels times 100,000 pixels. And it is really a challenge to view such images and also allow to analyze such huge images in an easy way. And the other question is also how to upload, organize and back up the large amounts of data such images have. Managing large amounts of image data is another question, because most of the time research involves really a large number of different images. So most research projects do not work only on a single image, but on a number of images. And the next question for research teams is always how to organize the data and the images to find things again and also to allow collaboration. That leads us also to the next important topic for research, which is collaboration. Most of the time there are teams collaborating in some way on research projects, so there also needs to be collaborative access to the data and also to analysis results. When involving multiple users, audit trail and traceability really become an important topic for quality assurance and accountability, especially in certain regulatory environments that apply international quality standards like the good clinical practice or the good manufacturing practice, the quality of the data used for research must really follow high standards, which may even be legally binding, depending on the use case. And the final and most important thing or challenge for our customers is they must produce results. So there are always the same recurring questions in research, for example, determining the number or the location or the class of an object on an image. And at the moment, most of the time, those questions are answered by manual analysis of images. And especially if you think of large images like those gigapixel images I stated before, this is really a labor-intense work, and it may even take hours or even days to work through such a huge image. And the result of such an analysis done by a human is most probably subjective and also has a high risk of being of containing errors. And at the same time, the teams need to ensure that the results they produce are reproducible, and also the results they produce should be accurate, and this work should be done as fast as possible. So there is really a huge number of challenges when you need to produce results or analysis results on images manually. So yeah, there's really a lot of questions for our customers in relation to efficient image analysis, and we set out to solve this. Our founders both have a strong background in medical sciences, in digital imaging, and also in machine learning, and they experienced a lot of those challenges during different software projects in the industry. They saw an immediate demand for a product supporting management and automated image analysis of large-scale image data, and started thinking of the IKOSA platform as a product in 2017. In autumn 2018, we finally set out on our journey to develop IKOSA as a platform, and since then we expanded our portfolio to be able to support whole processes in life science research from end to end. So a full workflow from the microscopy sample to the analysis result of an image. Starting with the digitalization of an analogous microscopy sample with IKOSA iSticks, to the direct upload of image data to IKOSA portal, where you can organize the storage, view the images, annotate images, and also manage your analysis results, to the automated analysis of images with IKOSA Prisma, which provides algorithms based on machine learning. And in the end, we are also providing an open API that allows a seamless integration of our whole platform for users with their systems. And based on some thoroughly crafted decisions, the core parts of all of this portfolio heavily rely on an event-driven microservices architecture, implementing CQRS, domain-driven design, and event sourcing. But before talking about the rationale why we have chosen this architectural approach, I want to finalize my introduction to our domain by giving you a brief demo of an image analysis workflow in our platform. For that, I have prepared a sample project in our platform. The project is about the example I have given you in the introduction of my talk about this tumor growth measurement. And first of all, we start out by uploading some images we took with our microscope and have scanned. And while the upload is running, I'd like to show you or give you an impression of the size of such an image by showing you a whole slide. This is a whole slide showing cancer tissue, and you really see you can zoom to a really high level of resolution, And at this level, you can identify cells, and our research teams can also then annotate certain sections in this image and, for example, mark a cell as having a high or low level of this certain protein. And when those cells are marked, we provide the researchers also with a functionality to review those annotations, we call them annotations, in another context. So to see or cells that have been classified as having a low protein level or having a high protein level, or also, for example, things that are classified as false positives or false negatives, for example. So this really gives power to the user to see the data they annotate also in another context. And the final thing I want to show you is the automated image analysis. We are providing algorithms for different use cases, for different standard research questions. For example, also this tumor growth quantification. And I now choose one of the images I just uploaded before and let our machine learning algorithm do its job. Depending on the size of the image, this job could take from some 10 or 20 seconds up to really minutes or even hours if it's a whole slide image. And when the job is finished, as you see now here, we can finally just download the result and open it and see, for example, the result visualization, which shows us that it detected the bluish and the brownish cells automatically. And there is also a quantitative result in a CSV file, for example, that allows for automated processing of this result. So I think you've now got a good impression on the challenges of the domain in which we are working. And now I would like to dive into the rationale why we have chosen to rely on event-driven microservices, on event sourcing, and also on CQRS to build IKOSA. So let's board our time machine, mainly powered by Confluence pages, Git commits, and Jira issues. You know this type of fuel. And let's revisit some of the main decisions we have taken in the last 2 years and what we learned along the way implementing those decisions. One thing we quickly learned and that helped us all along the way is the importance of decisions. Software architecture, you know that if you are developing software, is really crossroads everywhere. The important thing is you need to take decisions consciously. Consider all your available options and take a decision, and then also document it. There is nothing more harmful to software architecture than a rash or unconscious decision without considering any alternative options. There is really no excuses. Research, take the decision, and document it. There is a lot of decisions I remember where the process of researching and comparing the alternatives made the initial option in the end the least attractive. I think I actually wouldn't be talking on this conference to you if we did not consider our available options for the CQRS framework in the first place, for example. There is no guarantee that you will never come back to a decision, but having your options documented and also your decision documented helps solving doubts even 5 months later. And I'm also speaking out of painful experience here. To kick off the development of IKOSA, we did an agile chartering workshop, and we gradually developed the vision and mission for our system. And from that, we derived the main goals our architecture needs to support. And this is the main goals we got back then. First of all, we identified that we needed our platform to have a good horizontal scalability to be able to work in a cost-effective way. especially when you think of big image data analysis, we need a quite flexible software architecture that allows us to scale up and down our computing resources horizontally by adding more machines as we require it, because we cannot foresee when our customers having high loads of image analysis, and we don't want to hoard computing resources if they are not used, because they are meaning cost to us. The next thing we quickly identified was we needed portability to be able to support on-premise deployments. We knew from the start that we wanted to provide our platform as a software as a service, but we also knew our customer segments, and especially, for example, in the pharma industry, we knew that customers would really prefer to have their data and their research output on their own premises. So we knew that we needed to be flexible on the deployment of our solution. The third thing I already stated in the challenges of our domain is the audit trail. So when we are talking about collaborative research, especially with multiple users accessing the same data, quality assurance and accountability really play an important role. And for some contexts, for example, if you think of an analysis algorithm as a medical device, or this software as a medical device, it may even become a legal obligation to have this audit trail available. Another thing we identified was that we wanted to publish our APIs and publish a comprehensive API for third-party integrations to allow our customers to integrate with their systems. And since we have foreseen that this API could become really complex, we need to maintain and develop our API specifications and documentations in a really easy way. And the final thing, really important for us as a startup, was we needed a quick time to market to really fast gain business traction. There were already competitive players on the market when we started development, and as a small team with limited resources, we really needed to be able to deliver fast. Up to this point in time, no one of our team really had got in touch with CQRS or event sourcing before. We were doing CRUD style microservices for some time, but apart from that, we really were newbies to the event sourcing and CQRS topics. So for us, it was decision time, and we started researching our options on main architectural patterns we should apply to fulfill our architectural goals. And we quickly also came up with some solutions for the main parts. So first of all, we found out that microservices, and especially the 12-factor app paradigm postulated by Adam Wiggins, really was a good way to develop portable components. So counting on containerization and this microservices pattern and 12-factor apps allowed us to provide scalability and portability at the same time. The next thing, supporting our goal towards a comprehensive public API, was that we identified we need to go with an API-first approach with generating the code from an API language, more or less, because this would allow us to really maintain the API in one place and generate our clients and server stubs from that point, and allow us to really, in a simple way, maintain a complex API. The next thing we identified, supporting our goal towards a quick time to market as a small team, was we needed to go with DevOps, because this is the logical consequence for a small team handling a complex system. Lots of automation and staging and change management really allows to quickly deliver high quality software. And boom, there it was, the final solution that we took, that changed everything. We quickly identified that CQRS and event sourcing would be a fit for our requirements regarding scalability and also the audit trail. We quickly saw that CQRS is really a good fit for the scalability, and since event sourcing is naturally a good fit with CQRS most of the time, we also saw that this could be a good enabler for our audit trail requirement. The two main risks we saw with event sourcing and CQRS and domain-driven design from our state of research at the time was that it would add really more complexity in the backend compared to a simple CRUD style application developed as a system of state rather than a system of events. And the other thing was that we expected it to have really a great influence on our user interface and also on the user experience design compared to a CRUD style application, especially regarding the eventual consistency problem or the latency in the write and read models. But yeah, in the end, the advantages on scalability and audit trail weighed out those two risks, and we decided to go down that road and count on CQRS and event sourcing, where we are handling domain data. Since we already had some existing CRUD components for common tasks like a user management and authentication framework, we decided to stick with the CRUD pattern there, because especially in the case of our user management, it would be really over-engineering to rebuild the whole system with CQRS and event sourcing. Another important but also quite logical decision we took already at that time was that the actual binary data for the images must be handled outside of the events and only be linked into the events by reference. So the stage was set, and we imagined lots of decisions still ahead, and the first thing we needed to do was to find a tech stack that would support our chosen solution approach. Most of the stack was clear quite soon. Regarding the DevOps, we were already used to Jenkins and GitLab CI for automation, and we also have chosen to count on Docker Compose and Kubernetes for configuring and orchestrating our deployments as industry-proven technologies. For the API-first approach and the code generation, we saw that OpenAPI proved to be very mature, and together with the API generator, it really became a perfect match to maintain the whole API for us. And for the microservices and the 12-factor app paradigm and also containerization, we counted on Java, on Spring Boot and Docker. Those technologies were also set because of the available competencies in our team at that time, and of course also Docker as the de facto industry standard for containerization. Finally, the thing we had to find was a framework that supported event sourcing, domain-driven design, and CQRS. And again, you guess it, it was decision time for us. A short disclaimer is suitable before I explain our decision on the event sourcing and CQRS framework we should use. We are not receiving any benefits from Axonic, and we are not affiliated with them in any way. In general, we were looking mainly for frameworks in Java, since again this best reflected the resources that were available in our team at the time. We had Apache Kafka, Akka, and Axon Framework on our shortlist, and at the first quick research, Kafka was the most probable candidate to us. But we stick to our process and really researched our options. For Kafka, we soon discovered that we would need to implement a lot on our own. And yeah, there is a nice blog post about event-driven architectures with Axon and Kafka from Vijay Nair. He's also having a talk at the conference. You should really check out if you want to find out more about what Kafka can do and what not in relation with event sourcing and CQRS. But for us, it was the decision to cross Kafka out from our shortlist, and that left Axon and Akka for us to decide. Since both frameworks were mature at that time and also had a rather comprehensive documentation, the decision was mainly taken on two facts. The first thing was the tight Spring Boot integration of Axon, and the second thing was the more focused scope of Axon on event sourcing and CQRS opposed to Axon, which really had a much broader focus on the whole framework. These two factors gave us really more confidence in a steep learning curve with Axon. And in the end, after having implemented everything, we also can confirm that. One thing we have foreseen with both AK and Axon was a kind of a vendor lock-in effect. So when we would go down that road, it would not be easy to switch the framework anymore. So we would need to stick to it. But since both frameworks were open sourced at the time and had an active community and active users, we did not see a real risk in that. With those important decisions settled, we set course and sailed off for implementation. And there was plenty of wind, you can bet on this. For the rest of my talk, I now want to recap two early evolution phases of our platform, and I want to explain you some of the challenges we faced during those evolution phases. The goal for our MVP was to allow uploading, organizing, and viewing large images in our platform. So we started out with a rather simple domain model that allowed us to store images in projects. So there, in the first place, was no real hassle in the slicing of the aggregates, and it was rather simple to design the domain and the events. Regarding the building blocks of our architecture, we initially started with a single application for the command and the query part, and we used the Axon Mongo event storage engine and an in-memory query model without any persistence, which meant we used the direct representation of API DTOs as the query model. So we really stored the DTO objects or the API objects in an in-memory map. And we also did a replay of the whole model at every restart of the service. And this really gave us a quick and painless development at the beginning. So we didn't have to mess around with object relational mapping or with database schemes or with maintaining a database for the query side. This was fine for us, and it really helped us kicking off the development. But soon we identified the need to separate the query and the commander part, because for the commander part we started introducing our first sagas, and we started introducing different configurations we needed for the commander and the query side. And so we needed to split the commander and query into two separate components to gain more flexibility in the deployment and configuration of those parts. Since we have foreseen that and the split went quite smooth, we have kept all of the code for both commander and query side in separate packages, and it was a rather painless configuration work, more or less, I would say. Driven by the split of the command and the query part, we also got rid of the Mongo event storage engine and moved on to the then new Axon server 4.0 in that case. This provided for us a dedicated event store, and the other thing which was really nice was it provided a nice messaging infrastructure that easily allowed for us to distribute commands and events over multiple application instances, which in the end also, again, was great for scaling our application. Since we wanted to collect feedback really early and gain traction as soon as possible, we released our IKOSA MVP just around 3 months or 4 sprints after the kickoff of the development, and it worked. It had value for our customers, and we got feedback from real customers. One feedback, for example, was we want more features. We were prepared for that, of course. Our backlog was still full of features. So the journey continued, and with the following releases, we started adding really additional functionality that helped our customers to use the system for their research. For example, by adding annotations and allowing to put a label on such annotations in an image. With these new features, the domain model was starting to get more and more complex. For example, we were adding a huge relation. So between images and annotations, you remember the example before for this tumor counting in the cancer tissue. So those images can easily contain thousands to 100,000s of annotations. And also the relation between projects and images was larger than we expected in the beginning. So we already had production projects that had really 50 to even 500 or 1,000 images, which then also multiplies the number of possible annotations within a project, which then really comes into huge numbers. And it was decision time for us again, because we needed to decide how we can keep the aggregate structure clean while staying really performant and aligned with our API design. The main driving factors for this decision have been the size of the relation. I explained that before. So imagine 2 millions or 3 millions of annotations within a project. And the other factor was our API design. So we wanted to provide flat out REST APIs, so resources that are not nested to easily support also cross-parent queries. For example, imagine querying all annotations of a project. And again, we started to weigh our options. The question was, should we use multi-entity aggregates or distinct aggregates for each of our domain entities? And yeah, the most accurate answer to this was, it depends. Because there are downsides for both of the options. A multi-entity aggregate would represent the nature of the domain better. This means there is one aggregate that contains, for example, that is the project, and this aggregate would contain all the images and all the annotations that belong to the project. The downside is this would really lock the project when you add sub-resources or modify sub-resources. So commands that are sent to nested resources, especially in the case of annotations, for example, will lock the whole project. And for event sourcing, when using event sourcing with such a multi-entity aggregate, you will really get a huge number of events per aggregate instance, because all of the annotation events and the image events and the project events of a project will go into that project. And when you do event sourcing without snapshots, that will really add a huge performance penalty on reconstructing the state. On the other hand, using distinct aggregates, so separate aggregates for projects, images, and annotations, would allow independent operation on the aggregates, but at the cost of additional effort for validation. For example, you need to check if you create an image that the project exists. Weighing this trade-off between distinct and multi-entity aggregates, we decided to go for the distinct aggregates at that time, mainly driven by the performance and by the size of the relation, because we really imagined that to be a huge problem. Now, nearly 2 years later, we also already introduced our first multi-entity aggregate, because it really fit well. So we did not dogmatically make all of our aggregates distinct, only those that fit the use case. So you see, it really depends. To allow cross-aggregate validations with our distinct aggregates, we needed to introduce some simple validation projections on the command side. For example, as I said before, to verify that the parent project existed before creating a child image, or that an image existed before creating an annotation. That seemed to be a fairly easy task at first glance, so we simply implemented an event handler that updated the projection on the command side and stored some information into a database. Our service layer then could use the projection to check the existence of the parent project, and everything was fine. With that decision settled and the new features implemented, we released our next IKOSA version, and we were able to really add support for annotating images, which was again great for our customers. And then eventual consistency struck, really like a lightning. Having more usage on the staging and production system started revealing consistency problems soon after this release. So we experienced when deleting a project and at the same time creating an image within the project, we did rely on the validation projection to be up to date. What we didn't consider was that our validation projections were implemented as asynchronous event handlers. So our validation projections got consistent only eventually. For the Axon users among you, we simply used an event handler, and the configuration defaults to a tracking event processor, which is asynchronous. So when creating a child entity, like an image, we were requesting or validating the existence of the parent from the validation projection. And the latency of the validation projection when processing the parent deleted event may cause a child created event to go through even if the parent was already deleted, because it simply was not updated already. And yeah, having little load on our production system during development, and also not having a test case forcing that situation artificially, the validation projection was always fast enough in our staging systems, and we simply didn't see that, that error or that condition. What we did to resolve this was actually moving the decision on creating a child aggregate to its parent via a command handling. So we have taken inspiration on that from the Axon Google group, and especially also on an article from Daniel Whittaker about set-based consistency validation in CQRS. And what we did was, since at least for Axon Framework, the commands of an aggregate are handled synchronously per aggregate instance, so only one command is handled at the same time, we can be sure that the child is either created correctly or the creation is denied if we route the create command of the child through the parent. There is no inconsistent state in between, because the validation of the existence occurs in the parent aggregate, and if the parent aggregate doesn't exist, the create child would not occur at all. And this mechanism can also be applied for other use cases where some child aggregates operation needs to be validated with the parent state. So, for example, when also cascading operations down an object tree. As an additional mechanism to make the validation projections consistent immediately, we changed the validation projections to be updated synchronously. For the Axon users among you, again, we were doing this by simply switching the validation projection event handlers to subscribing event processor. The validation consistency was resolved, but we still had another pain to resolve, with additional requirements for more sophisticated queries to implement features like cursor pagination or pagination for our annotations, and also row level security, for serving these huge amounts of annotations efficiently. The in-memory query model we initially used got more and more unpractical. So we decided to switch to a persistent query model based on a relational database. Up to then, our in-memory query model really worked well, and we also had it in production. And up to then, we did only store unrelated query DTOs. Because of that, we could really do rather fast parallel processing on the query side, because it did not matter if the project already existed when we stored the image or when we created the image. For Axon users, again, a quick information, we used tracking event processors with a sequential per aggregate policy, which means that all events that belong to a single aggregate instance are processed in the order as they appear in the event stream, but among different aggregate instances, all of the events can be processed in parallel. When designing the database scheme for our now persistent query model, we did this as usual, as we were used to from CRUD style applications, with referential integrity in mind, making sure that the project, for example, must exist before the image is created. A consequence of this was that the parallel processing was not possible anymore, because we needed to make sure that the project already existed in the query model when creating an image. In the example shown, this means that the event C must not be processed before event A is fully processed and committed in the query model, because otherwise C will fail with a referential integrity constraint. To resolve this, we needed to switch to a full sequential policy to process the events in the query model, to make sure that all of the events in the event stream are processed according to the global order. By routing our create commands through the parent aggregates, as explained before, when we were fixing the cross-entity validation, we could be sure that the global order of the event stream was fine, because we could be sure that the parent created event has been published before the child created event. With increasing size of our event stream in the production and staging systems, by now we already recognized that this change really comes with an increasing performance penalty on the query model due to this sequential processing. So we are not really happy with that at the moment, and the root cause for this was one unconscious decision we have taken, and this was that we included the referential integrity on the query model. And yeah, we are currently reworking everything, and we are trying to get rid of the referential integrity in the query model again. So this was a quick recap of some of the evolution phases of our image analysis platform. You see, we have encountered really a lot of challenges in the last 2 years working with event sourcing and CQRS. And yeah, what did we learn from this view into the review mirror? First of all, I already stressed that throughout my talk. So it's really important to be aware that architecture is really all about decisions. So it's really important to take every decision really seriously and research your options, decide and document, even if it's at first glance a small decision or a clear option. Try to research other options, because sometimes you really will be surprised. A big learning for us really was that domain-driven design, event sourcing and CQRS is a mental challenge, especially when the team is all new to it. And that was really true for our team. So we were really into CRUD style applications. And in the beginning, designing aggregates and events did not feel very natural to us. And the first aggregates and events also had a slight notion of CRUD style, I would say, when looking at them now. But getting more and more used to the patterns, this really got better, and we are now more into designing really flows of event. Two things that may help taking that initial hurdle of this mental challenge could be, first of all, trying to facilitate the design process of the events and the aggregates really with a structured approach. Adam Dimitriuk is having the keynote at the conference, and he is proposing the event modeling approach, and this, I think, would really have made the process really easier at the beginning. So if you're interested in this, of course, check out his talk. And yeah, if you're trying to start, try to use or facilitate the design process with some structured approach. And the second thing I can recommend is using some framework with a clean API that really supports learning the concepts of a pattern like event sourcing and domain-driven design. Especially in our case, when the team was really new to the topic, it really helped a lot that the API of our framework literally gave a good frame for the paradigm by itself and made it really hard to do things wrong. It doesn't need to be Axon framework. I think there are also alternatives out there. But for us, it really did the job well because of the documentation and also really because of the API. And yeah, keep away from reinventing the wheel. So implementing things on your own, rely on a framework, because there is really simply too much to consider for it to be feasible for implementing it on your own. And one thing we learned from starting with our in-memory query model at the beginning was that integrity is really important on the command side, and you can really keep the query side simple in terms of the model and keep it really lightweight. It really helps to ensure the integrity on the command side, and this is enough. If you ensure integrity on the command side, the event stream will be consistent, and the query model should really be optimized for reading and not for integrity. And finally, one thing we learned is don't be too dogmatic, because most of the time it really depends. Lots of learnings for us in the last 2 years of working with event sourcing and CQRS for me, and also for my team at KML Vision. And yeah, for us, the journey still continues. I hope you enjoyed the talk, and some of our learnings also have value for you in your projects. In any case, I'm really grateful for any feedback on our approaches, and I'm really looking forward to your questions in our live Q&A.